Diamagnetic materials have atoms or molecules with parallel and anti-parallel magnetic moments randomly distributed in such a way that their resulting magnetic moments in the grouping are almost zero. To explain the properties of diamagnetic materials, we will assume that all elementary particles of the structure of matter exhibit an experimentally determined magnetic moment. Since the magnetic moment of the electron is about 3 orders of magnitude greater than that of the proton and neutron, we will focus on it. In diamagnetic substances, the effects of the magnetic moments of electrons balance each other, so the resulting magnetic moment of the diamagnetic is minimal to zero. According to the basics of the ring theory, we can associate the structure of the electron with a current loop, and its magnetic moment can be defined in terms of the current and area of the electron. The direction of the magnetic moment vector is determined according to Ampere's right-hand rule. If we put a diamagnetic material into a homogeneous magnetic field, the instantaneous values of the magnetic field are superimposed in the matter on the ring structure of electrons, the resulting direction of which is opposite to the direction of the external magnetic field. This will reduce or increase the magnetic moment of the electron model according to the direction of its orientation. The consequence is also a reduction or increase in the size of the current. The external magnetic field exerts a force on the rings of electrons. The vector of this force is perpendicular to the direction of the external field in a homogeneous magnetic field. Since the magnitude of the forces is the same in both directions, the influence of this field will not manifest any major force effects. However, diamagnetic materials are characterized by being expelled from an external inhomogeneous magnetic field on a macroscopic scale, for example near the ends of a solenoid or bar magnets. To explain this phenomenon, we can choose a model of a ring of electron, through which an electric current, I, flows, and is placed by its axis in an external inhomogeneous field. At the location of the ring of electrons, the external magnetic field with induction, B, forms an angle, theta, with the normal. In an external inhomogeneous field, the direction of the force is parallel to the vector product of magnetic induction and the differential length of the partial part of the loop, and is perpendicular to it. The direction of the vector of this force is determined according to Fleming's left-hand rule. If the induction lines of the external magnetic field enter the palm and the fingers indicate the direction of the current, then the thumb shows the direction of the vector of force exerted by the external magnetic field on the ring with the current. For an external homogeneous magnetic field, this vector is perpendicular to the magnetic induction vector, and the force in the direction of magnetic induction and the z-axis is zero. If we use a ring of an electron with an oppositely oriented magnetic moment, the force will be oppositely oriented with respect to the direction of the magnetic field strength and the z-axis. Due to the magnetic induction of the external field, the magnitude of the force will be greater for the ring with anti-parallel magnetic moment. If the electron of an atom of a diamagnetic material is located outside the axis of an inhomogeneous magnetic field, the forces at opposite ends of the loop will act unevenly. Since the force exerted by the magnetic field on the ring of the electron is a function of the theta angle, the force, F1, in the z-axis will always be greater than the force, F2. If the magnetic moment of the electron model is anti-parallel to the external magnetic field, magnetic induction will increase the current, I, and thus increase the effects of the force, F1, and F2, in the z-axis by the magnitude, delta F. When the magnetic induction vector of the electron model is parallel to the external magnetic field, the resulting magnetic moment of the electron model decreases. The resultant magnetic force decreases and the magnitude of forces, F1 and F2, decreases by the magnitude, delta F. If electrons with parallel and anti-parallel magnetic moments are equally represented in the sample, then the total force in the z-axis will always be greater for the anti-parallel orientation of the magnetic moment relative to the external magnetic field than for the parallel orientation and will therefore be repulsive. If the orientation of the magnetic dipole changes, and thus the orientation of the external inhomogeneous magnetic field, the orientation of the forces acting on the ring of electrons also changes. In the axis of the magnetic field, or at a greater distance from its source, the magnetic field will be almost homogeneous in the z-axis, and the force in the z-axis will be small. The value of the force component, F, in the z-axis at a greater distance from the z-axis will be greater than the value of the force closer to the z-axis. For an inhomogeneous magnetic field of a magnetic dipole, the force acting on the electron is always repulsive regardless of the orientation of the magnetic dipole. More information about ring theory at www.ringtheory.eu. Thank you for your attention and keep an open mind.